Newton's law of universal gravitation, section 11.2 and 11.4. State Newton's law of universal gravitation. Well, okay, now that is the technical way it is described, okay, in most textbooks. We'll simplify it in just a minute. So basically what we're looking at here is we're looking at the force of attraction between two masses separated by the square of the distance between them. Okay, what is the meaning of R and of the negative sign? Well, basically the force is opposite the radius vector. And R hat, that little value R hat right there, is the unit vector that essentially points in the direction of mass 1 to mass 2. Now, what is the equation for the acceleration due to gravity on a planet? Well, if you take the idea that, first let's take the idea, and I'm going to write this in a simplified way. The gravitational force is equal to big G times little m times big M over R squared. And also recall that this is equal to little mg. So I'm going to substitute this right over here. Okay, and I get little mg is equal to big G, little m, big M over R squared. And you can see the mass of the object, the mass of the smaller object cancels, and we are left with little g, the acceleration due to gravity on a planet, is equal to big G, which is the gravity constant. The gravity constant, by the way, is approximately 6.67 times 10 to the negative 11. It's a very small value. You don't need to memorize it. But it's little g is equal to big G times the mass of the planet divided by the radius of the planet squared. Okay, circular orbits. Consider a mass m in a circular orbit of radius r from the center of mass m, where the mass of the center is so much greater than the mass of the object orbiting. Determine an expression for omega for such an orbit, right? And omega would relate to your angular velocity. Okay, so what we can say for this is that a gravitational force, which if you remember is big G, little m, big M over R squared, is a centripetal force, which is mv squared over R. Now, wants to write it in terms of omega, so let's remember a couple things. V is equal to R omega. So V squared would just be R squared omega squared, right? So let's go ahead and plug in for that. So I have mv squared over R equals G little m big M over R squared. Okay, and here's what I end up with. I'm going to substitute for V squared, and I get m R squared omega squared over R equals G little m big M over R squared. This is going to cancel with one of these, and we are left with m omega squared R, is equal to big G little m big M over R squared. So for omega, we would divide by R, so now it's R cubed. Little m is going to cancel on both sides. And omega, when we square root, is going to be equal to big G, big M over R cubed. Section 11.2, Binary Star Problem. Now consider that M is less than but comparable to big M. Both objects now circle their common center of mass. The mass big M makes a circular orbit of radius r, big R, about the center of mass, and the little mass M makes a radius little r. The total distance between the two objects is d. All right, so let's take a look. Their common center of mass is this dotted line right there. So the total distance between the two objects is d. Okay, you can see that this big M is orbiting a distance of big R away from their common center of mass, and the little m is orbiting at a distance little r away from their common center of mass. Okay, so what is true about this? The center of mass is the same for both stars. That's why it is called a common center of mass. Okay, and center of mass is equal to mass times distance over the sum of your masses. Okay, so if we looked at that, okay, we would get the fact that we have mass big M times big R. Okay, that's the center of mass for the bigger one. Okay, and then technically it's divided by big M over little m equals little m times little r. Big Mister equals little Mister, right? Divided by the same common, but that's going to cancel, right? So ultimately what we end up with is the fact that big Mister equals little Mister. Okay, big mass times big radius equals little mass times little radius. Okay, now we have an expression from earlier. If you recall, take this expression from earlier, which says that omega squared is equal to big G, big M over R cubed. Okay, and we're going to kind of rearrange some of them. And so I'm going to actually move this on over, because if I go back to where that derived from, m omega squared r was equal to big G, little m, big M over r squared. But r squared is the distance between the two binary stars, and that would be distance d. So that's a d squared. So what I'm going to do now is I am going to substitute, okay, notice little m cancels. Okay, so now let's solve for omega. Well, solve for omega squared first. We have to divide by the radius. And so we get omega squared is equal to gm over d squared, but then you're dividing by r, so dividing by r. Okay, now we're going to use the equation to the right, but we're going to do the following. Okay, it's gonna we're gonna take that common center of mass, and this mass, right, is going to be the mass of both stars. Okay, so in other words, this becomes omega squared equals G times big plus little m star. But if you're combining both, then you have to basically make this little r has to be the same as distance d. So in other words, d cubed. Okay, so show that if mass big M, if the big star is so much bigger than little star, the expression for omega reduces to essentially this, because if M is so much bigger than this, then this essentially goes to 0 compared to that. And so this equation reduces to right, that essentially goes to 0 if it is so much smaller than big M. And so omega squared is just simply big G, big M over d squared. And at this particular level, if big M is so much bigger than little m, then that means the distance between them is approximately the same as the little r distance. Right, so big M plus little m is approximately just big M, right? And we end up with this approximation here. Section 11.3, gravitational potential energy. Recall the following: that work is the integral of force dx. Okay, remember, work is equal to a parallel force times distance, right? Now, this would be a variable force function. This is a constant force. Okay, also recall that work is equal to a change in kinetic energy. Therefore, changing kinetic energy is the same as a negative change in potential energy. Therefore, we get a negative work or a negative force dx. Use the last fact to find an expression for the gravitational potential energy. Okay, so let's start with that. U is equal to negative, and I'm going to go from infinity to, so from super, I'm going to bring in objects from super far away to r infinity to r equals big R, which is essentially the radius of the planet. Okay, and I have to plug in for the force function, and then I'm going to be deriving with respect to r, so it'll be dr instead of dx. So I'll be plugging in negative g little m big M over r squared. Okay, that is with respect to, well, let me just plug this in right here this way. So big G little m big M over r squared dr with respect to r. Okay, so recall these are all constant, so let's bring them out front. So this becomes U is equal to the negative G little m big M integrated from r equals infinity, super far away, to r equals the surface of the planet at radius away. Okay, and what you're left with is 1 over r squared, which is just r to the negative 2 dr. Integrate that, and we get U is equal to negative G little m big M times r to the negative 1 . Okay, and I forgot the fact that this should be negative, right? So that cancels. But when we divide by a negative 1, evaluating from infinity to little r, we get negative G big M little m big M, sorry. And then we're going to evaluate, first we're going to evaluate big R and then infinity. So it's going to be 1 over big R minus 1 over an infinite distance away essentially goes to 0, which is nice. And you're left with U is equal to negative G little m big M over R. This is the gravitational potential energy that is more universal, right, for any distance r away, not just at the surface of the Earth. Okay, this right here is just the surface of the Earth. How far must two objects be if they have zero potential energy? Well, infinitely far away. Infinitely far away, the potential energy goes to zero. So if r is infinity, the whole fraction essentially goes to zero. Why must potential energy become more negative as two objects get nearer? All right, so let's think about it this way. When an object does what it wants, the potential energy decreases. When two masses get closer, the fraction value gets greater. Therefore, the only way to make U decrease is if the fraction is negative. We can see it from a picture format. The equation mgh and the idea that U is equal to 0 on the ground is merely a linear approximation of true gravitational potential energy function. Remember that if we set any point at any location equal to 0, since potential energy has no physical meaning, only a difference or a change in potential energy has physical meaning. Okay, so this part of this linear function that you see right here with mgh really is just, it's a linear approximation of that tiny little bit right there. Okay, so again, if this is the surface of the Earth, and you're setting the surface of the Earth at potential energy equals 0, okay, that means that some potential energy, some infinite distance away over here, has to be, we have to essentially be negative potential energy as we get closer and closer to the radius of the Earth. Section 11.3, escape velocity. Consider a small mass, little m, and a large mass, big M, subject only to their mutual gravitational attractions. Assume that little m is much smaller than big M and the objects are at distance r apart. You know, kind of like a rocket taking off of the Earth. The rocket is significantly smaller in mass than the Earth is. Write an expression for the total mechanical energy of the mass. So total mechanical energy is equal to kinetic energy plus potential energy. Okay, which would be 1/2 mv squared plus a negative g little m big M over r. Okay, now what does it mean the small mass escapes to a larger mass? When to have enough escape velocity means you have to have enough kinetic energy to reach a point an infinite distance away from the larger mass, so that the larger mass's gravitational force goes to 0 and the smaller mass will not fall back to the larger one. Okay, and by the way, so we can keep going with this, what must the small mass's total energy be if it is to escape the larger mass? Well, to reach an infinite distance away, the potential energy has to increase to 0, because remember, the potential energy is negative at the surface of the Earth and it goes to 0 farther and farther away. Okay, this means that there must be enough kinetic energy that can turn negative potential energy into 0 potential energy, essentially. Therefore, the total energy must be 0, just enough kinetic energy, right, to escape. So you set that total energy equal to 0. Okay, and that's where we begin. We're going to write an expression for it. So 0, the total energy, is equal to 1/2 mv, I'm going to say escape, v escape, squared, is equal to minus g little m big M over r. Okay, we're going to let that equal 0. I'm going to add this over to the other side, and we get 1/2 mv escape squared equals G little m big M over R. And then just go ahead and solve the equation for V escape. And we get an expression, the escape velocity is equal to the square root of 2 times G times the mass of the planet divided by the radius of that planet. Section 11.1, 11.2, and 11.3, Kepler's laws. Kepler's laws describe the work done by Johannes Kepler in the late 1700s. Let's review Kepler's laws that relate to planetary orbits. Kepler's first law. All of the planets move about the sun in orbits that are ellipses, where the sun is at one focus. Now, an ellipse is very similar to a circle. But it has 2 focus points. Now, what makes an ellipse interesting is that if you take any 2 points, so say for instance I take this point, the distance from that focus point to, let's say, that point on the edge of the ellipse, and this focus point to that point on the ellipse, and I add those up, we call this pathway 1 and pathway 2. Pathway 1 and pathway 2 will always add up to the same amount no matter where you are on the ellipse. So for instance, I could say here, let's say that point right there. If I added up this point plus this point, that would be the same as 1 plus 2 on the other side. So the sum of the distances to any point on the edge of an ellipse from both foci is constant. That's what creates an ellipse. Now, the law here is saying that planets orbit the sun where the sun just happens to be one of those ellipses. In reality, if a small mass m is subject to a gravitational field of a larger mass m, where m is significantly larger than little m, then the trajectory of the smaller mass will be a conic section. Which one depends on the total mechanical energy of the object in its orbit. In any case, the larger mass resides in the conic section's focus. Okay, now these are some possibilities. However, Kepler's first law describes elliptical orbits. Now, truth be told, even though the orbits are elliptical, they're circular enough. Okay, what that means is if you take both, so if this is our one focus point, and this is our ellipse, if we bring those focus points together, closer and closer and closer, what do you get? You get a circle. Okay, a circle is nothing more than an ellipse that has 2 focus points joined together at one center. Most of the planetary orbits, even though they are elliptical, are circular enough for Newton's law of universal gravitation obviously is going to take place because it's universal gravitation, but it's circular enough to apply centripetal forces at various points along the way. How about Kepler's second law? A line connecting the planet and the sun will sweep out equal regions of time in equal areas. Okay, so what does that mean? So let's say this right here is a 10-day period. And let's say this is also a 10-day period. And let's say that's also a 10-day period. Equal times sweep out equal areas. when we're talking about a line that's drawn from the sun to one point in the orbit to the other point in that particular orbit. Equal times sweep out equal areas. This law is actually a statement of the law of conservation of angular momentum. The proof is that the total area of a circle is pi r squared. The region A, right here, would be 1/2 r squared theta. Now, how do we get that? Now, we have to remember, we're working with radian measurements here. If we were working with degree measurements, the area of a sector, right, is theta, whatever the angle is, divided by 360 degrees times pi r squared. That's if it's in degrees, but that's not what we're doing here, okay? So the other formula that describes the area of a sector is given right here. And that's 1/2 the radius squared times the angle in radians. Therefore, this in any tiny area would just be 1/2 r squared. Instead of theta, it would be d theta. And Kepler's second law essentially states that the changing area with respect to time is constant. Think about that. Equal times sweep out equal areas. Okay, well, let's prove this. Let's start by taking our statement here, which is this. If dA dt is constant, then 1/2 r squared d theta dt is constant. Well, let's do something about this. The first thing I'm going to do is I'm going to go ahead and multiply both sides by 2. Just move the half for the other side. And we have r squared. And then I'm going to rearrange our values here. D theta dt equals 2 times whatever your constant is. Now, recall, what is d theta dt? That would be omega. So far, what do we have? We have r squared omega equals 2 times a constant. Now let's go ahead and multiply both sides by the same orbiting mass. Okay, and this becomes m r squared omega equals m times 2, or 2m. I'll just rearrange stuff here. There we go. Now, recall that mr squared, what is mr squared? Oh yeah, mr squared is the rotational inertia, right, of a point mass, orbiting something else, times omega equals this value of 2m times a constant. What does that mean? Angular momentum is constant. Kepler's third law is a ratio of orbital of orbital period to orbital radius. Specifically, we discover the following. Okay, and we're actually going to prove it first before I show you what we discover. Okay, let's start off with this idea here. Gravity is a centripetal force. Okay, start there. Now, I'm going to rewrite this with our equations, right? So our gravitational equation would be G m over r squared, that's our Newton's law of universal gravitation formula, is equals mv squared over r, where little m is the orbiting body and big M is the bigger object that's being orbited, in this case a star. mv squared over r is our centripetal force. Well, a couple things are going to happen. Cancels. One of these factors cancel. And recall that v is equal to r omega. Therefore, v squared is going to be r squared omega squared. And we're going to substitute that right there. So now we've got big G, big M over r equals r squared omega squared. Okay. Now, how's that useful? Wow. Recall that omega is equal to 2 pi over the period. Therefore, omega squared would be 4 pi squared over t squared. So I get Gm over r equals r squared times 4 pi squared over t squared. Now here's what I'm going to do to kind of clean things up, because really what I want orbital period as a function of orbital radius. Period as a function of radius. That's our orbital period is our dependent variable, orbital radius is our independent variable, okay? So that means I got to solve the equation for this. And I can do that by multiplying both sides by r, okay? Dividing by, if I multiply both sides by r, I get Gm over 1, so I guess just Gm, equals r cubed times 4 pi squared over t squared. And now I'm going to swap those, and I get t squared is equal to 4 pi squared r cubed over g times big M. And that, guys, is your Kepler's third law formula that relates orbital period to orbital radius. And specifically what it says is the square of the orbital period is proportional to the cube of the orbital radius. Let's see what we got here in this picture. It's kind of shown here in the picture. 4 times the radius, right, is actually 8 times the period. Now you can relate this to different stars with different orbital periods by just setting up a proportion. And that in that case, you would just have t squared to t squared, r cubed to r cubed, and it's object 1 to object 2, object 1 to object 2. Just set up a proportion if you're comparing two different stars or planets with different orbital radii and different orbital periods. For elliptical orbits, the ratio of t squared to a cubed is the same for all objects orbiting the sun, where a represents the length of the semi-major axis. Non-circular orbits, section 11.2 and 11.3. When dealing with non-circular orbits, there are two equations that can be considered. One, conservation of mechanical energy. Conservation of mechanical energy is just telling you that energy initial equals energy final. You'll have kinetic energy because planets are always in motion, and you'll have changing potential energy because potential energy, if you recall, is equal to negative big G, big M, little m over R. The other equation that's very useful for these kind of orbits would be conservation of angular momentum. Li equals Lf. Now, since a planet is considered to be a point mass orbiting a star, we're looking at L equals mvr in that form of the equation. So you end up with mvr equals mvr. Well, the mass didn't change, but when the star is over here, for instance, and it has a very small radius, I'll call it radius 1, versus over here when it has a much larger radius, we'll call that radius 2. Well, just like a figure skater who brings his or her arms in close to their body, if the rotational inertia or the mass distribution gets smaller, well, the rotational velocity increases. Well, that's no different when it comes to this as well. Smaller radius, tangential velocity is much faster. Larger radius, tangential velocity, much smaller. Now, with this equation here, since the mass of the planet never really changed, we just focus on the velocity and radius. And so the equation really becomes V1R1 equals V2R2. You're just comparing the velocity and radius at one point in an orbit to the velocity and radius at another point. Perigee is the point on an orbit that's closest to the sun, perihelion for the sun. Apogee is the point on the orbit that is farthest from the sun, aphelion for the sun. Consider a spacecraft that is in an elliptical orbit. To increase the total energy of the rockets, the spacecraft, the rocket should be fired to exert a force on it in a direction that is tangent to the orbital path. The greatest increase in energy will be accomplished if the rockets are fired closest to the Earth's sun. Let's take a look at this example. This example, for the most part, comes straight from at least a couple different AP exam questions that come to mind. It says we have an object orbiting a planet of mass big M in an elliptical orbit as shown. 3 points in the orbit are marked as A, B, and C, where the object had distances RA, RB, and RC respectively, and speeds VA, VB, and VC respectively. The only orbital data known about the object is as summarized. RA is 1 times 10 to the 8 meters. RB is 5 times 10 to the 8 meters. VA is 2,700 meters per second. And VC is 300 meters per second. Using that given information, let's figure out the following. Let's figure out the distance, RC, and let's figure out the mass of that planet. Let's also figure out the speed, VB, and the angle through which it is rotating. Okay, so to do RC, let's think about what we have so far. We have RAVA, and we have VC. We're looking for RC. So we can use this equation here and compare VA, RA to VC, RC, and then just solve the equation for RC. That's exactly what we're going to do. So RC would be VARA divided by VC. So VA was 2,700 meters per second times RA, which is 1 times 10 to the 8 meters per second. And we're going to divide that by VC, which is 300 meters per second. Okay, so now when we divide by a smaller number, obviously the whole fraction, the whole value gets bigger. And that makes sense because RC is a very big number. Okay, throw that in your calculator. 2,700 times 1 times 10 to the 8 divided by 300. You should have gotten a value pretty close to 9 times 10 to the 8 meters. To find the mass of the planet, we can use conservation of energy. And how do we do that? Well, total energy remains constant at any 2 points. So what do we know? We know mass and radius. Well, we know mass of the spacecraft is little m. Now, we don't know what it is, but you'll see that has a canceling effect. We don't really need to know it. But here's what we do know. We know VC, RC, and we know VA and RA. So what we could do is we could set the total energy at A, for instance, equal to the total energy at C. Now, recall, guys, that total energy is kinetic plus potential, okay? So let's try this. We have the kinetic energy, which is 1/2 m times VA squared, okay? Now, also recall that your gravitational potential energy is negative big G, little m, big M over R. Okay, so when we're adding, you're really subtracting that, right, that negative potential energy. So minus, so it's 1/2 MVA squared minus big G, little m, big M over RA. Okay, that right there is the total energy at position A. Okay, and that's going to be equal to 1/2 MVC squared minus big G, little m, big M over RC. Okay, so let's start solving this thing. Let's go ahead and multiply everything by 2. And notice there's a mass term. Let's divide everything by little m. Okay, going to cancel all the little m's. And cancel the 1/2. Then what I'm going to do is I'm going to rearrange the terms. I'm going to take VC, well, let me rewrite it first. So we have VA squared minus 2G big M over RA okay, and that's going to equal VC squared minus 2 big G M over RC. Okay, and so what I want to do is I want to be able to basically bring the two GM terms together, because remember, we're solving for M. So I want to bring those two M terms together. So I'm going to add this over here, which means I will have to subtract this term over there. So let's rearrange the terms. And we get VA squared minus VC squared equals, then at this point, I can go ahead and factor out my mass, because that's really what I'm looking for. So if I factor out my common mass, then what I'm left with is 2G over RA minus the 2G over RC. And if I just divide both sides by that, right, you're going to have a value for mass. And I want you to practice plugging in for that. Okay, VA, what was VA again? VA was 2,700. So we're going to go 2,700 squared minus VC was 300 squared. Okay, there's our numerator. Our denominator is going to be 2 times your value for G. Recall G is the gravitational constant of about 6.67 times 10 to the negative 11. Now, you don't need to memorize that number because it's given to you on the table of information and the formula sheet for the AP exam. So we're going to go 2 times 6.67 times 10 to the negative 11 over RA. What was RA again? 1 times 10 to the 8. Okay, and then minus 2 times 6.67 times 10 to the negative 11 over RC, which was considerably longer. We found that just a few moments ago at 9 times 10 to the 8 meters. Okay, go ahead and take a second to plug that in your calculator. You should have gotten a value very close to 6.1 times 10 to the 24 kilograms. So ultimately, it was conservation of energy that helped us with this problem. Well, we're trying to find speed B. What do we know? Now, for the speed VB, I would love to say that we could use conservation of angular momentum and just compare VARA to VBRB. I would love to say that. The problem is, when you're dealing with angular momentum, it is the, let me go back to the basics here. The angular momentum of a point mass is mvr perpendicular, where you have a perpendicular component. Well, here this velocity is, we have a perpendicular radial component to velocity. Here, you have a perpendicular radial component to velocity. But here you don't. The radius is coming in at this angle. We would need that, okay? And that's not something we have at the moment. So, or we would need the angle, meaning it's really VARA sine theta. Because remember, when you're talking about a perpendicular angle, sine of 90 degrees perpendicular is 1, which just gives you that. Equals VB RB sine theta. Well, we don't know what theta is, right? In fact, actually, if you look, that's exactly what we're looking for right here. So it seems to me that this would actually be what we want to do or what we want to use, right, in this part of the problem solving right here. Let me section off this work here. There we go. But it's not going to help us for this because we don't know that information just yet. But what we could do is we could use something similar to what we did in the last part. To find the mass, we use conservation of energy. Well, mechanical energy is conserved everywhere too, regardless of the radius. You don't need, the beauty of conservation of energy is you don't need vector components like we did for angular momentum, okay? We just simply need energies, and that's exactly what we're gonna do. So let's use conservation of energy again. This time we'll compare the energy at A to the energy at B. Okay, which would be 1/2 mVA squared minus big G, little m, big M, all divided by RA. That's going to equal 1/2 mVB squared minus big G, little m, big M over RB. And we'll try to keep this segmented a little bit here. I know the problem's getting kind of messy. Do what we did last time. We multiplied everything by 2, right? Multiply everything by 2. Okay, and we canceled all the masses, right? All the little masses. All right, and that, if you recall, gave us VA squared minus 2G big M over RA, and that's equal to VB squared minus 2 big G big M over RB. And you're basically solving the equation for VB, which means you have to solve for VB squared, okay, first. So the way I see doing that is take this term here, add it over there, and start plugging in your numbers. And then you can square root at the very end. So VB will actually be the square root of VA squared minus, and we can factor out a lot of stuff here. 2GM is common to both terms. So I could factor out a 2 big G big M, and then what's left over is 1 over RA minus 1 over RB. It'll just make it easier to plug into that. Okay, so VB would be 2700 squared minus there we go. 2700 squared minus 2 times 6.67 times 10 to the negative 11 times the mass. Remember, we figured out the mass in the previous part of the problem. It's about 6.1 times 10 to the 24. Okay, and then we're just going to multiply that by 1 over RA, which was 1 times 10 to the 8, minus 1 over RB. What was RB again? RB was 5 times 10 to the 8. take a second to throw that in your calculator. I would chunk that up into bite-sized pieces, make it easier on yourself. As I look at this, I see that I have one thing a little bit backwards, and that is if I add this over here, the B term is actually first and not the A term, which will affect how your answer comes. And that should make sense because this minus this would give you a negative number, and you can't take a negative square root. So that right there was my obvious check that I did something wrong. Hopefully you noticed the same thing. There we go. Okay, now try and plug that in your calculator. Okay, we should have gotten about 900 meters per second. And finally, to find that missing angle theta, we can now use conservation of angular momentum to solve the problem. And we're going to solve for sine of theta and then take the arc sine of that to get the angle. So here's how we'll do that. This sine right here is going to be 1 because that's 90 degrees. So the sine of theta that we're looking for on the right side of the equation is really VARA, over VB. It's the ratio of your VRs to VAs. Ratio of your VA time VRs. There we go. Okay, so sine of theta is equal to VA is 2700 times 1 times 10 to the 8 over VB is 900, we just figured this out, times, keep writing VB, that should be RB, which was 5 times 10 to the 8. Now, you don't need a calculator for this. 900 goes into 2700 3 times, 10 to the 8 cancels, and you're left with 3/5 is what you're left with. So sine of theta equals 3/5, which is 0.6, taking the arc sine of that. Okay, now taking the arc sine of that, we get 37 degrees. Okay, however, one of the things that we should note is that's 37 degrees beyond, and we have to look at the picture to actually see that. It's 37 degrees beyond 90 degrees. Look at the picture. Theta is this whole angle right here. Okay, what we just found is this little section right there. There's your 37 degrees. Well, you got to add it to 90. Again, note that Sine of that angle is 37 degrees. The angle labeled in the diagram is clearly the supplement. Okay. Oh, my mistake. That's right. The supplement, if you guys recall, is plus theta equals 180 degrees, right? 180 degrees is the supplement. So I have to subtract that from 180, which would be 143. There we go. I thought that angle looked a little bit too shallow. Section 11-4, the hole to China problem. Okay. Consider a non-rotating, perfectly spherical planet of radius r, total mass m, and uniform density. This, of course, doesn't exist. That's why it's ideal, right? Okay, now we say a hole is drilled through the center of the planet, and the object of mass m is dropped into this hole from rest at the surface. Later, the object is a distance r from the planet. Write expressions for the following. The mass m sub r, that is within the radius of the planet. Well, because the planet is uniform density, let it set up a density ratio. So remember, density is mass per unit volume, right? Okay, so here's how we'll do that. We'll go mass mr, okay, per unit volume. Now, volume, if you recall, is 4/3 pi r cubed. Okay, I'm talking little r for that one. But what I'll do is I'll just, set up a proportion with that, with the entire planet, with m and then 4/3 pi big R cubed. Okay, obviously the 4/3 pi part's dropped out. That's equal on both sides. And y'all can see what we're left with here is a nice proportion that relates the mass of the inner part, so to speak, per radius cubed to the mass of the whole planet divided by the biggest radius cubed. And so if we solve for MR, it's going to be M times the ratio of your radii, of the cubes of your radii, which really represent the ratio of your two volumes, if you think about it. The gravitational force exerted on mass little m. Okay, let's start with our gravitational force equation. F equals big G, little m, big M, R, sub r, over little r squared. If we make some substitutions, in other words, we can substitute our value for m sub r. And we get big G, little m, over r squared times big M, r cubed, over big R cubed. Okay, let's break this one down. That would be, let's see, 2 of those would cancel with 2 of those, leaving you with 1 left. And your gravitational force would be big G, M, big M times R, over R cubed. Is the motion simple harmonic? If so, find an expression for omega and t. Well, remember what satisfies simple harmonic motion. A has to be relatable. A has to be proportional to omega r, or omega squared times r. Okay. In fact, if I'm being exact about it, it's A is equal to a negative omega squared r. Okay. Well, technically, the force is a negative force because the expression is F is equal to negative big G M. This is just the magnitude of it. Okay. If we include the direction of the force vector itself, it's pulling back towards the planet. It's the negative direction. So big G, little m, big M times r over r cubed. Okay, and we are trying to make it fit this description if it's truly simple harmonic motion. So this, right, is going to be ma equals negative big G, little m, big M over r cubed, little r. You can see that's going to cancel. Okay, and I've got little r over here already. And let's see what we get from here. We have A, the acceleration is equal to negative big G M over r cubed, and then times r. Well, it turns out that this is actually equal to omega squared. And the way we can actually prove this is go back to what we learned from Kepler's third law. What we derived a moment ago is that Kepler's third law relates the square of the orbital period to the cube of the orbital radius. So recall that t squared is equal to, and remember, t is equal to 2 pi over omega. So that means omega is equal to 2 pi over the period. So keep that in mind. So you have t squared, which obviously means t squared is 4 pi squared over omega squared, right? Okay, so we've got t squared equals, it was 4 pi squared r cubed over big G big M. Okay, now what I'm going to do is I'm just going to substitute that for that. Okay, and we have 4 pi r, or 4 pi squared over omega squared equals 4 pi squared. You can see our stuff's already getting ready to cancel, huh? Over GM times r cubed. Okay, and this is, I'm being sloppy with the r's. This is big R here, the radius of the orbital radius there. Okay, now look at what happens. Cancels. I'll leave a 1 up there. And if I kind of solve this thing for omega, then what I get when I take my cross products this way is I get omega squared r. If I take my cross products this way, I get GM. So, I'm sorry, I have r cubed. So I have omega squared r cubed. There we go. Okay, so what I'm going to do is I'm going to divide both sides by r cubed. And there you are. Omega squared is equal to GM over r cubed. And if we look at that, is exactly what we have right here. GM over r cubed. So what we have is A is equal to negative omega squared r, which is our recipe for simple harmonic motion. So long answer, yes, it is. Now, consider instead that the object is shot from just above the hole such that the object makes a circular orbit that just skims the surface of the planet. Will the object take more, less, or the same amount of time to reach the other end of the hole? Okay, so to figure this out, what we'll do is we'll just set up an orbit, okay, where the gravity force is going to be a centripetal force. So we can go, we can go this way instead. So instead of going mv squared over r, remember the other way to write it was m omega squared r. That's the other way to write a centripetal force. So I'll do that. M omega squared r is equal to big G, little m, big M over r squared. We'll go ahead and divide both sides. Little m's cancel. And again, remember we said omega squared was equal to what? Big G, big M over r cubed. Okay, and so what was that telling us? That means omega is equal to the square root of gm over r cubed. And recall that this is equal to 2 pi over the period. So 2 pi over the period equals the square root of gm over r cubed. Well, I think what I'm going to do right now is I'm going to take the reciprocal and flip both sides. So t over 2 pi would be equal to the square root of r cubed over gm. And then last step, multiply by 2 pi. Okay, so this is our relationship. Now let's go back to the question asked. Will the object take more time, less time, or the same amount of time to reach the other end of the hole? Well, what is time dependent on? Time is dependent on the mass of the planet and the orbital radius. So the same period exists in both cases. Therefore, same time. Consider the same planet again, but this time the hole is drilled off center. The hole's closest approach to the center of the planet is a distance d from the center, and the sides of the shaft are frictionless. Write an expression for the component of the gravitational force that is parallel to the shaft. Okay, so let's see. Well, we can begin with the idea that the gravitational force inside the planet, okay, is our F sub g, and that's a negative. I'm gonna use the full expression this time, including the direction. Negative big G, little m, big M, over r cubed, little r. Remember, we derived this earlier, okay, earlier on in the problem. Okay, now what we're going to do in this case, because I really want to be able to got this we're going to multiply both sides of this equation by x over r. And that ratio right there. you see we end up with negative big G, little m, big M, x over r cubed. Again, why did we multiply by this x over r ratio? Because what we're looking to try and do is we need a gravitational force component that is parallel to the shaft. Okay, so let's look back at the picture. So here's the shaft that we're talking about right here. We need a component. We need a component that's parallel to that. So x over r, if you think about it, x over r represents the sine of the angle, which would be a parallel component. Write an expression for omega for the simple harmonic motion exerted by the object. So F is equal to negative big G little m, big M, x over r cubed. Okay, and again, you're going to replace this with MA. And that's equal to negative big G little m, big M, x over r cubed, cancels. And again, what do we know? A is equal to big G m over r cubed times x, where this is d squared x dt squared. This is omega squared, right? And that's x. Right? And that's your simple harmonic motion equation right there. So it fits. Same period and omega for the shaft as through the center of the planet. Okay, final section. Planet destruction. When a planet forms, particles of mass coalesce into a sphere because of their gravitational attraction to one another. The particles begin very far from each other so that they have zero potential energy. When the particles come together, they now have negative potential energy. Remember how that works? Negative potential energy close to the surface of the Earth or surface of a planet, zero potential energy very far away. So as you go farther and farther away from a planet, your negative potential energy becomes less negative, getting closer to zero. Well, when the particles come together, again, they now have negative potential energy. That means lost potential energy became another form of energy. Well, that would be kinetic energy of the rotating planet, or heat thermal energy. The potential energy that is released is called gravitational binding energy. Well, in order to destroy a planet, that gravitational binding energy has to be returned to the planet so that all of the particles of mass can be returned to an infinite distance away from each other. In other words, where it started. Keep in mind that the gravitational binding energy is the minimum amount of energy required to move all particles of the planet so far from each other that they do not recoalesce into a planet again. Okay, in other words, gotta move them far. It's kind of that escape speed concept, right? These particles have to escape each other, escape any gravitational pull that they might recoalesce. The actual amount of energy required to destroy a planet is much greater, since energy also required to break chemical bonds that hold atoms of the planet together. Consider a perfectly spherical planet of total mass m and radius r. Divide the planet into shells of mass dm and thickness dr. Each shell is a different radius r from the center of the planet. Write an expression for the mass, the differential mass dm of the shell with radius r in terms of the entire mass of the planet and radius r, and mass little r, which is the radius of each shell, and dr, the differential radius thickness. Okay, well, how about let's start with the idea that density is equal to mass per unit volume. Okay, so mass is density times volume. And recall that volume is 4/3 pi r cubed. So dV is equal to, if I were to derive that, bring this out in front, subtract, what do you get? 4 pi r squared dr. Well, what is that? That's the surface area, isn't it? Okay. And then here, if I were to derive this, dm would be rho dV. And we've got a value for dV. So dm is equal to rho times 4 pi r squared dr. Okay, now I can rewrite this a little bit and also note that rho of the planet is mass per unit volume. So what we have is we have dm is equal to rho, which would be mass per unit volume, times 4 pi r squared times dr. Okay, so we're almost there. Recall that the volume was 4/3 pi r cubed. And you could think of this as like 4/1 times pi r squared. And 4/1 times 3/4, those are going to cancel, right? The pi's are going to cancel. One of those factors is going to cancel. This is radius. This is big R cubed. This is little r squared. And so what we end up with is the differential mass is equal to 3 times m r squared dr, and then just over the r cubed that's left over. Each shell of dm, okay, the small differential mass, is peeled off of the remaining mass left on the planet. It takes a certain amount of energy, du, to remove each shell an infinite distance away. Determine the differential energy required to remove the shell of mass dm, that is a radius small r thickness, from the planet's surface to an infinite distance away. Okay, if you remember the ratio of volumes, look that up from the previous part of the problem, and that's little m is equal to big M times the ratio of the volumes, right? Which was r cubed over big R cubed. Okay, and what I'm going to do at this point, we're going to rewrite it as follows. Using what we just got there. I don't know if you see it. So we'll come back to that part. We know that U, if U is equal to negative GM over our dm replaces little m. And so what would du be? Well, it would be big G, mass of the planet, dm over r. Okay, and all I'm going to do is substitute that for that. Okay, now what was dm? Remember what we wrote over here? We're going to substitute that too. There's a lot of substitution going on here. G over little r times big M over little r cubed over big R cubed times 3 times the big M over little r big R cubed times little r squared, dr. Okay, so all of that was your dm. Okay, now, if you clean things up a bit here, you'll see big M, there's big M squared. Okay, you'll see that you have, let's see, r to the 5th power, but you're dividing by one factor of r, so that would be little r to the 4th power. So we have little r to the 4th power. We have big M squared. I see big M squared. There's a 3g that we can account for there. And we're not canceling anything there, so it's just divided by big R to the 6th power. There's our dr. There's our differential equation for the du. Determine the total energy U required to remove the planet. Well, to figure out U, you have to integrate this. So we take our equation, du is equal to 3g m squared r to the 4th over big R to the 6th dr, and we just integrate both sides. Okay, so you're going to integrate, the integral of du, of course, is u, And we're going to be integrating from r equals 0, which is the surface of the planet. Let me see. So we're going to basically integrate from the center of the planet to the surface of the planet. Okay, now if you notice, there's a bunch of stuff here that's just constant. All of this is constant and just comes right out front. You're really just integrating r to the fourth power, which is really easy with respect to r. Okay, so we're going to pull the 3 big G, big M squared over r to the sixth power, and then we're integrating from 0 to r of r to the fourth power dr, which would be 3 big G M squared over r to the big R to the sixth power, and that's r to the fifth power over 5, evaluating from 0 to r. Plug in the big R first. Well, you only need to plug in the big R because you plug in 0, it cancels. And so plugging the big R first, we get U is equal to 3 big G M squared R to the sixth power times big R to the fifth power over 5. And you can see that 5 of these factors of R are going to cancel with 5 of those, leaving you with 1 left over, which means we just end up with 3 G M squared over 5 R. And that represents the expression for the total energy needed to remove the planet's mass. Okay, so now if we were to plug in actual values here, if this were, let's say, the Earth, big M would be about almost 6 times 10 to the 24 kilograms. Radius R would be about 6.3 times 10 to the 6 meters. And the binding energy would be about 3.74 times 10 to the 32 joules. This would be enough energy to increase the temperature of a Earth mass solid iron ball. Let's pretend that Earth is a solid iron ball. It's not, but let's just kind of pretend that it is. But anyway, it would be enough energy to increase the temperature of this quote-unquote Earth mass solid iron ball by about 139,000 Kelvin. Okay, again, note that Earth is only about 32% iron. So this is obviously an idealistic example, but it's done so with simplistic, idealistic conditions. Obviously, planets are not made from homogeneous structures. They're very their densities are changing, especially the rocky planets. The big gas giants usually have icy cores at their center.